ChatGerry, Math Physics Medicine, MPM, and Viscoplastopology, VPT, Differences, Similarity, and Evolution. Part 2. Number 1458, VPT Sharp 021, December 5, 2025 2130. Gerald C. EclaireMD Foundation. Category, Medical Research Methodology. This second part explains why viscoplastic medicine theory, VMT, and topological data analysis, TDA, naturally evolved into one unified framework that I now call VPT, or viscoplastopology. The goal here is conceptual clarity. A step-by-step technical VPT procedure will be presented free as the second part of my article. My medical research focuses on mortality diseases caused by long-term metabolic damage. My MIT advisor, Professor Norman Jones, spent his career studying catastrophic collapse of structures. Although biomedicine and engineering appear different, both involve extreme events where statistical averages hide critical danger. Traditional biomedical research relies heavily on averages and regression. But death is an outlier event, not an average. Chronic illness is nonlinear, time-dependent, and irreversible. My work focuses on the real drivers of mortality, not the statistical middle. Medicine has historically been descriptive rather than quantitative. Medicine training emphasizes memorization, protocols, and hierarchy, not mathematical analysis. When I describe biomedicine as a system that should be explained numerically, I do not criticize the field. I am pointing out that tools such as VMT and TDA can enrich clinical understanding by revealing the shape, energy, and time-dependent behavior of chronic diseases. VMT and TDA come from different academic roots, but they share a deeper logic. VMT, grounded in physics and engineering, describes how stress inputs deform a system across time, creating irreversible change measured by cumulative energy. TDA, grounded in geometric topology, describes how data points form shapes, how those shapes deform, and how connectivity patterns evolve. One measures energy, one measures geometry, yet both describe nonlinear, dynamic, path-dependent systems that do not reset. This makes them ideal for studying diabetes progression, cardiovascular decline, kidney injury, and stroke risk. It also explains why VPT works beyond medicine. Over the past year I applied VMT, TDA, or VPT to psychology, personality disorders, economics, business strategy, political science, life science, zoology, and music cognition. In most domains, these methods reveal deeper insights, because they study patterns, not categories. VPT methodology overview. Data preparation begins with normalization. Most biomarkers follow a simple rule: higher values mean worse condition. Physics follows the same rule: higher load and energy level increases danger. Geometry also follows this logic. Stable shapes are compact, unstable shapes are stretched, bent, or fractured. Therefore, I normalize each input by dividing it by an ideal reference value. This creates normalized inputs. For VMT, normalization of the output is optional. For TDA, normalizing both output and inputs improves the clarity of geometric patterns in graphic demonstrations. After normalization, values typically fall between 0 and 5, where 1.0 is the healthy reference. VMT model. VMT starts with one output and several normalized inputs. The first step is calculating the rate of change of the output, which I call the strain rate, the most important element of this model. Multiplying each strain rate by its corresponding normalized input produces a stressor value. These stressor values allow us to draw a stress-strain curve across time. Using calculus, we compute the area under this curve. This enclosed area is the viscoplastic energy, or VMT energy. It reflects cumulative damage from repeated stress inputs. From this, we can calculate each stressor contribution percent, and the cumulative damage percent across time. VMT therefore measures how chronic stress inputs bend the system, slowly but irreversibly. It is a macro-level description of burden and damage. TDA model. TDA also starts with one output and multiple normalized inputs, but it analyzes geometry instead of energy. We construct a multidimensional data matrix, compute covariance, and derive eigenvalues and eigenvectors. Eigenvalues represent the magnitude of variation. Eigenvectors define the direction of deformation. We then project the data into low-dimensional manifolds, usually 2D or 3D. In 2D, deformation is measured by the area of the data cloud. In 3D, deformation is measured by the enclosed volume. These geometric spreads mirror the VMT energy concept, but express it through shape instead of stress-strain integration. After projection, TDA examines data connectivity. Data points that travel together indicate stability and strong internal linkages. Points that separate or form gaps indicate instability or transitions. This reveals clusters, loops, holes, and discontinuities that statistical methods cannot detect. A simple way to visualize topology is to compare basic shapes. A small smooth ball is very stable. because its shape spreads weight evenly in every direction. In contrast, a large polygon with sharp corners is unstable, because its pointed edges and uneven surface make it harder to rest in one steady position. Even a small push can shift or tilt it. TDA therefore measures how the internal shape and structure of the system evolves. VPT model, VMT TDA. When combined, VMT provides the energy story and TDA provides the geometric story. Both belong to the broader family of pattern recognition. VMT explains cumulative burden. TDA explains geometric deformation and connectivity. Together, they create VPT, a unified model capable of explaining irreversible system evolution in medicine and beyond. Conclusion. After writing 1,458 research papers, including more than 700 VMT papers, and over 50 TDA papers, the boundaries between physics, engineering, mathematics, and medicine disappeared. VPT is the natural outcome, a single framework that studies how systems deform, adapt, and sometimes collapse under repeated inputs. At age 79, I finally understand that knowledge, not achievement or recognition, is the true source of power and survival. My research today is not for journals, but for life itself. After my stroke, research became my therapy, my stabilizer, and my way to help others understand their own health risks. If even one person benefits, then this work has meaning. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is for educational reference only and not medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All rights belong to Gerald C.